I've seen some very interesting artifacts and bugs in the last couple of days. A couple of people I queued in the lab to ask me something, yeah.
Our LCD stops updating once we increase the sampling frequency higher.
Right, so there's a symptom where the LCD stops updating when you jack up the utilization CPU in the interrupt service routine, because main doesn't get a chance to execute anymore. And so the code necessary to update the LCD croaks. Now, one possibility is don't update the LCD unless the human does something. As long as the human isn't pushing a button, don't update the LCD. And then you won't notice the lag because it won't be happening. Is that what you ended up implementing?
Yeah, but it was still pretty slow. So.
It's still pretty slow, but that's okay. Slow's okay.
If you switch the compiler to the O3 instead of OS, you save a lot of cycles.
Yes. The default optimization, if you go to the project config panel, near the bottom of the main window there, it gives an optimization level which defaults to OS, which means something like optimum trade-off of speed and size. But if you want to go for maximum speed, you go to O3 optimization, and it chops, what, 30% of the code out. Now, so that gave you more cycles in the interrupt service routine to get stuff done. The downside of increasing the optimization level is everything gets less forgiving. If you mistake a volatile for an int, or vice if you do anything weird that is not syntactically correct, it will be optimized away. And so if you go to O3 optimization and you say, that's funny, it doesn't make sound anymore, then probably you made a syntax error or a logical error that is eliminating the variable of interest. So you have to be a little careful with it. But it will save you up to 30% of the cycles. Sorry, 15% of the cycles. And O3 optimization, the compiler writes better code than I do. I've been doing assembly for a long time. It's better. Any other comments or questions? If you're using carpless strong and you get weird, unpredictable state variable changes, it's probably because your pointer structure is incorrect in the circular buffer. And you're marching out past the end of the circular buffer and stomping all over memory.
And in the report, we have to mention the CPU load. So
yes.
How are we going to measure that?
How can you get the number of cycles you're in the interrupt service routine? Did you notice I put a timer in the interrupt service routine?
Yes, timer 2.
That's how you do it.
So we just print it out.
Sure.
Okay.
So you turn on timer 2 at the beginning of the interrupt service routine. You turn it off at the end, and then you read it out. You read out tcount2 in main and print it. And that'll give you the number of cycles you're in the interrupt service routine, but not the number of cycles it takes to get into the interrupt service routine or out of it, which you're going to have to find out by counting cycles in the assembler listing. So you're going to go to the .lss file, it's in the default directory, the .lss file for your project, and you're going to do a search for ISR, and then you're going to count how many cycles it takes from the time the interrupt service routine, from the time the event happens, the hardware event happens, the timer goes off, until the time you start executing your code. And you will find that it's a whole bunch of pushes, pushing all the registers that are necessary to save. And you can look up in the data sheet, each push takes 2 cycles. At the end of the interrupt service routine, there is going to be a bunch of pops that pop the registers back out. They each take 2 cycles. And then there's a return from interrupt, an RETI, which also takes 2 cycles. So when you add all that up, the number of cycles that you're in the interrupt service routine, plus the time it takes to get in and the time it takes to get out.
And then times the sampling rate.
Yeah, that'll
over
give you the
16
CPU load.
Okay.
The highest one I've seen so far is about 99%, which is pretty good. Between 95 and 99% simplicity.
Wait, so how much time does it take again to get into and out of the ISR?
It takes, to get in and out of the ISR, the raw hardware time, the time it takes to clear the hardware flag, push the program counter on the hardware stack, clear the I bit, and do an indirect jump to your through the vector table to your code is about 4 cycles or 5 cycles. But you also have to push a whole bunch of state. The state of the C compiler has to be pushed before you can go into the interrupt, because it's essentially a change of context. Right? It's a separate process that's running, and so every register that's not volatile has to be saved. You can look at the assembler and figure out what those are. What else? Yes.
For the additive synthesis, when you do the step count say take 1, you have 2 to the 16 divided by 8,000 times the frequency. Where's the 2 to the 16?
It's just 2 to the 16th count. 16-bit count. The direct digital synthesis unit is given by 2 to the number of bits over the sample frequency times the increment, right? Or have I flipped something there? The units are wrong.
That's just a property of the DES.
Yeah, you're overflowing a 16-bit counter, and every time you overflow the 16-bit counter is equivalent to 1 cycle. What else?
But how are you going to measure it from your memory? Because I think this is also another question asking like
Accuracy.
yes.
How would you measure the accuracy of a frequency? Well, you could get pitch pipe. You could get out a pitch pipe and do beat frequencies. But probably most of you, yeah. Go ahead.
Use the oscilloscope.
Yeah, the oscilloscope. The reason I chose 0.5% is that happens to be just exactly how good the oscilloscope is at measuring frequency.
But if we are using the FM synthesis,
Yeah.
does that mean that frequency is actually varying a little bit? Like
So what you're going to do to verify the frequency, since FM does vary the frequency, is you're going to turn the depth. You're going to turn off the FM. You're going to turn the depth to 15. And you're going to make the system slow enough that the oscilloscope can get a good estimate of the frequency, because to get 1% accuracy at 100 hertz takes 1 second.
okay.
So you're going to have to have fairly slow notes playing a long time. That's why you have to have a deterministic scale, so that you can go right up through the frequencies, play each note long enough that the oscilloscope locks into the frequency, so you can write down the frequency that it thinks it's hearing.
How many different frequencies should we measure for doing the accuracy?
How many different notes are you generating?
So we should measure each one.
Well, once you measure one, it's going to be pretty easy to measure the rest. But there's only 8. I think you could make the argument ratiometrically that if you measure a couple of them and they're right, then the rest are probably going to be right. What you are going to find, though, is if you go one cycle too long on the interrupt service routine, the frequency is going to drop by 1 octave. It's going to be off by a factor of 2 because you'll only take every other interrupt. And so you'll find that you'll be almost exactly right on until you're off hugely. So it should be easy to detect. Anything else? Yeah.
This is probably a dumb question again, but timer 2, when we're timing the amount of cycles in the ISR, you multiply it by 8 before you break it out. Why is that?
Because I had set the prescaler to time divided by 8.
On timer 2?
Uh-huh.
Is that in the...
I know in the actual code it's set to full speed. But in the printout I left it, and I think the reason for that is that I edited the code in between the two. I edited the code to take out one voice. And yes, I think you're going to probably have to pre-scale timer 2 by maybe as much as 32. Which means you can only get within 32 cycles, but that's close.
How do you check how much CPU is?
I just said that. I just explained that in detail about 2 minutes ago.
Well, I just can't.
Oh well. So, I'm sure you'll be able to find that video now. Tomorrow. Or maybe the next day. Oh well. What else? So let's go on to lab 4 then. So last time I did the hardware for lab 4, the sensor electronics and the motor drive electronics. Are there any questions on that? We're sort of overbuilding the motor control, and the reason for with opto-isolation and suppression capacitors and suppression diodes and all that kind of stuff. But the reason for overbuilding it is that if you use motors in your final project, you're going to be happy to overbuild it because you'll cut down on the debugging time immensely. No questions on the hardware. Let's go to the software side. I'm going to force you in this lab to use a multitasking operating system, tiny real time. Which you've probably never heard of before because it was written by 2 guys as an academic research project. Dan Hendrickson and Anton Servin. And their website seems to have disappeared. But code and by permission I grabbed the documentation before the site disappeared, so I had it. So I took Tiny Real Time, which was a really stripped down kernel, and a bunch of stuff to it. I ported it to the Mega 644. I added soft timers so you can have an arbitrarily large number of independent timers. I added mutex support, a trace facility. But the idea is it's a preemptive kernel. Preemptive kernel, and it uses earliest deadline first scheduling. At earliest deadline first scheduling. Did you cover this stuff in 3140? Earliest deadline? Okay. So the idea is that, so the way you're going to write a task here, the way you're going to write a process, or whatever you want to call it, a flow of control, is there's going to be some, it's going to be written as a C function, which is going to, let's say, call this task 1. There's going to be some init section where you set up the communication with the other tasks. There's also going to be some variable declarations here. So you're going to declare variables, which will then be defined on the stack of the tasks that you are defining. They will not be globals. They will be defined in the space of the task you are defining. So you're going to declare variables here. You're going to do whatever other init, and then you're going to fall into a while one loop, which never exits. The task functions cannot exit, must not exit. Now, there are various things you can include in this while one loop that signal the operating system to do things. For instance, you can force a wait. You can wait on a timer. You don't have to use timer 0. You don't have to maintain ticks, timer ticks. That's all done for you. All you need to do is say, I want to wait 30 milliseconds. And magic happens, and you wait, and you don't come back, you don't exit this call until 30 milliseconds is gone by. Actually, it's a little more complicated than that. You say, I want to wait a minimum of X milliseconds, but I have to be done by Y milliseconds. So there's going to be a release time at which you can execute, and there's going to be a deadline by which you must execute. A completely separate task is going to declare its own variables. It's going to do the init it needs. Drop into a while loop, which of course is going to never exit. And you can also other things you can cause this loop to yield control to the operating system by doing a wait on semaphore, and then maybe signal the semaphore later. So we're going to have multiple tasks. There's a scheduler and a task swapper. I'm not going to talk about that. There's a null task, and I wrote the null task as merely sleeping the CPU. So the CPU shuts down if nothing else is going on. If there's no active task that is scheduled and ready to run, then the null task runs, and the null task puts the CPU to sleep.
Sorry, that's waves. What's this?
Wait on semaphore. Yeah, it says like sample, doesn't it? Or the Snapple. Wait on a semaphore. Of course, each task thinks it owns the machine, but it's actually sharing the registers of the CPU. Each task has to have its own stack. So associated with this is going to be a stack and a stack pointer. So you say, okay, you change tasks, you have to save the state of the machine and the state of C. And on this particular architecture, that means that you have to store all 32 registers, all 32 8-bit registers. plus a few other variables of the state, the execution state, the deadline time, and a few other things, it turns out that you need a stack size of about 40 bytes minimum. So the stack is going to be a minimum size of 40 bytes. If you declare any variables, that size has to be added into the stack size. If you use printf in a task, you have to add 80 bytes to the stack size. Printf defines some big buffer that it uses to form strings. And this operating system is not forgiving. It doesn't check stacks. It does no bounds checks. So if you overrun a bound stack of a stack bound by putting a printf in a function without increasing its stack size, what happens is it crashes. Does a stack overflow? It walks across the next task in line or across the operating system structures and it hoses everything. So, when the system crashes, it's been running, you do something, it crashes, the very first thing you ask yourself is, oh, should I increase the stack size? Now, you're going to be running 2 or 3 tasks, probably for Lab 4. There's not going to be a particular memory budget that you have to live with, so give these tasks some stack space to begin with. Save yourself some tears. Just give it a couple of 100 bytes. So now let's talk about the schedule a little bit. We're going to be doing earliest deadline first. Every task is going to have associated with it a release time and a deadline. The release time is the earliest time it can execute, that you're going to allow it to execute. The release time is the first time that it's allowed to execute. The deadline is when it has to finish. Clearly, it is a bad idea to set those to the same value. Because then it has to execute in 0 time. And as soon as the release time occurs, it then becomes the highest priority task because its deadline is passed, and it'll execute until it's done, even if it is the slowest, lowest priority thing available. Therefore, you have to estimate the amount of time that is required for a function to run before its next wait state. Now, most of the stuff you're going to do in Lab 4 is very fast, except for updating the LCD. For updating the LCD, you need to make sure that you allow a millisecond per character between the release time and the deadline.
So the release time is just the start time.
The release time is the first time at which you are going to allow that task to run. So let's say that you want something to do. Let's say you want a task that's periodic every 30 milliseconds. Mm-hmm. But you really want it done within 40 milliseconds. Or 35 milliseconds, or whatever you choose. You don't let it run for 30 milliseconds, and you say, now it's your turn, and you need to get done.
So what are these times defined with reference to?
Current system time, which is a globally maintained counter that's maintained by the operating system, by the kernel.
So your current system time will roll over or
Ticks.
reset.
It's a long. It rolls over every day.
So you say, like, you know, if time is divisible by this, then that's the release time.
If time equals 30 milliseconds, if the time equals current time plus 30 milliseconds, then execute.
So it's kind of similar to that question. So the deadline's like 30, like time count 30, and it takes 20 seconds before the while loop waits. The next time, when will the next be scheduled? Because if something else comes in, then the deadline's already passed, and then.
If the deadline passes, it becomes the highest priority.
But then every time it waits, it's now the highest priority again.
If it is waiting for its next release time, so if you want highly precise times, you have to add X time to the last release time, not to the current.
Okay, so it's all relative to the last time it was scheduled.
Yes.
Okay.
I'm going to do some examples. I'm not just going to throw you into this cold.
I have another question.
Yeah.
About the semaphore stuff. Are those semaphores shared between tasks, or are they?
Semaphores are shared between tasks if you define them as global variables.
So they are global variables.
They would be global variables. Have to be global. Now, one aspect of preemption, of multitasking, is that no task can determine when it's going to lose the CPU. You got a question? No task can determine when it's going to lose the CPU, and so each task has to be pretty defensive about shared resource. Any memory location which is shared between two tasks has to be locked by the task when it is in use. This is particularly important for multi-byte variables like ints. You can get into the situation where you've stored part of the result, you take an interrupt, you store the first byte of the result, you take an interrupt, the other task modifies the variable, you come back, you write the other byte, but it's not part of the same number anymore because the other task wiped it out. And you can get inconsistent results. You must lock memory when you are using it, and the way you're going to do that is with semaphores. And probably many of you know this, but let's just go through it. So a semaphore is a integer value, and it's going to be defined. There's going to be a set of functions that modify semaphores. If you have a semaphore, a wait for semaphore in a task, then the wait is going to execute this. If the semaphore value is greater than 0, then we're going to decrement the semaphore and keep going. In other words, in a task that is waiting on a semaphore, if the semaphore has a value of 1, it will be decremented and the wait will not happen. It will fall through the wait and keep executing. It's important that this is atomic. It is atomic, meaning that no interrupt can occur during this two-part operation, this check and then decrement. So the function which implements the wait is going to turn off interrupts for a few cycles. It's going to turn off interrupts. It's going to do the test and decrement, and then turn it back on. So this is an atomic operation. You can never change tasks during that operation. If the semaphore is equal to 0, then we're going to have to stall the task and wait for a non-zero value. So that's the other part of this wait, is that you're going to have to, if the value in the semaphore is already 0, because whatever is modifying that semaphore in another task has grabbed it, then you'll just have to hang there until it's valid. I see perplexed expressions. Okay. When you're done using whatever memory or whatever it is that's being protected here, then you're going to signal the semaphore. You're going to signal the semaphore, which is to say you're going to add 1. And that also, of course, has to be atomic. Cannot be interrupted.
Is this all in the same atomic sequence, or are these like each one before each if, whatever, if?
Well, the interface to this is rather low level.
Mm-hmm.
So you're going to have to, if you want to access memory, you're going to have to do a wait on some semaphore, modify memory, and then signal the semaphore. You could write a function that does this, but you're going to have to wait on a semaphore, modify memory, signal the semaphore.
But all of that would be like before you do it, you would turn off the interrupts, and then after you.
No. These things turn off and on the interrupts. That's all hidden from you.
Mm-hmm.
Now, the nice thing about a home-written kernel is that you can go look at the source code. It's all there. You can hack the operating system. If you're brave and have lots of time on your hands, as I know you do. But the downside of a home-written operating system is that it's probably correct. But you can go look at the TRT wait function and see what's in there, and there is in fact a this includes a CLI call at the beginning, which is clear master interrupt bit, that turns off interrupts, and at the end there's an SEI, which turns on interrupt. Same for signal. So a lot of the things that you've been doing in lab are pretty predictable. You know how long it takes to write an LCD character. You know how long it takes to hold a keypad. The one thing that's really hard to figure out is when is the human user going to do something? And in this lab, I'm going to ask you to control the motor via the UART interface from PuTTY, from the PC. And that task can wait forever for the human to do something. So it's going to be sitting there in a scanf statement or something like that, waiting for input. And we can't kill the operating system, we can't kill the kernel just because one task is waiting. So the UART code has been modified. The UART code has been modified to not block. At the basis, the reason that the UART blocks is that there is a function called getCar, which by default, the version that you've been using in UART.c, the version you've been using in UART.c polls a bit. It polls the UART ready bit, data ready bit, to find out if a character has been received. And it just stays in a loop until there is a character there, and then it returns the character. And so if you're doing a scanf, it'll stay in that loop multiple times until you hit enter, then it'll build the string, and then it'll pass the string back through the calling routine. But at the basis of it, getChar is blocking. Normal getChar is blocking. So what I did was to write a non-blocking getChar. And what it's going to do, there's going to be some interrupt service routine, USART underscore, 0 underscore RX underscore vect. It's going to set a global variable TRT underscore RX underscore C. By the way, you should probably want to avoid variables that start with TRT because there's a few globals. All start with TRT. And we're going to set this equal to UDR0. UDR0 is the data register that contains the character which was just received. And then, so we retrieve the character that was just received, and we won't get here, we won't get to this interrupt until the data is valid. We won't get into this interrupt unless a character has actually been received. So we receive the character, and then we're going to do a TRT signal to some semaphore, SEM, RX, ISR signal, which is going to indicate to the operating system that the kernel that an interrupt has occurred, the data in RX underscore C is now valid, and the task which called getChar, in other words, the task which is waiting for user input, can now proceed. But while it's waiting, this task uses no CPU. On the transmit side, transmits are easier to handle in some ways because, again, you have a reliable time estimate. You know that 96 baud is going to take almost exactly a millisecond per character to send each character. So you can guess that it's going to take 25 milliseconds to transmit 25 characters. I modified the print at the bottom side. Printf calls a function called putChar, which is also blocking. The default is blocking because it waits for the transmit buffer to be empty and then transmits a new character. So I modified putChar to have a circular buffer. It can buffer, by default, it can buffer up to 200 characters. And it buffers them very quickly indeed because it's not printing them, it's merely putting them in a chunk of memory. So it means that your printfs become non-blocking until you print about 200 characters. Then there is at the bottom end of the circular buffer, you all know the circular buffer, right? There is a UDRE interrupt, UART data register empty, that says that I can transmit more data, and it sends another character out of the circular buffer unless the circular buffer is empty, and then it stops. So on the receive side, you have non-blocking serial communication because the task which calls git car merely relinquishes control to the kernel and waits for the next character. On the transmit side, you have a non-blocking system as long as you don't print more than about 200 characters, because you have a circular buffer which is very fast to fill. You can change the size of that buffer if you feel like it. You have all the source. So the effect is that a task which is waiting for a human or is printing to a human does not slow down the kernel or any other task which is running. That means you can have a human-oriented task waiting in a scanf command, waiting for input, for C input, and the control loop for that, or the control loop which is running the motor can run at full speed. Without doing anything special, without coding, without you having to do any coding, it should just work. So you write the printf, as long as you link up trt uart.c rather than uart.c, then you'll get the new git car and put car, and it'll just be transparent. It should just work. Assuming I did it right. I tested something. Quite well. So what questions are there? I'm seeing a lot of kind of, oh my God, looks. You need, one thing for this lab you really, really need to do is you have to go to the TRT page and read it. Really read it. This is you can't do just-in-time reading here. You have to read it top to bottom. Because there's lots of ways of messing it up. All the data structures are static. That means that if you want 6 semaphores for your program, you better allocate memory for 6 semaphores. If you don't change the default allocation, which is for 4 semaphores, and you ask for 6, something is going to get wiped. So you need to know how to set all of the configuration variables, and that's all explained on the TRT page. I'm going to go through part of it in lecture, but you really, really need to read that page. There's a bunch of utilities. For handling time. In the context of tiny real time, you should never have to manually set up a timer to time milliseconds. You should never do that. And the reason I'm hitting that hard is I've seen people do it a lot. Read up on the functionality of the kernel and use it. Somebody else has done a bunch of programming for you. Use it. It's easier. I'm asking you to do something easier, not harder. In addition to the basic kind of wait function which says, don't stop execution on this task for a while and then start again later. There's also virtual timers you can define, which allow you to do one-shot timing or periodic timing. They record how many times they've overflowed. They record their status. They will signal a semaphore for you to toggle another, to cause another task to execute. They're very flexible. Use them. Don't roll your own. Question?
So you said before that you can only have 4 semaphores to change the number. So does that mean that they're predefined for you, these semaphores, pre-allocated?
There is a file called trtsettings.h that has in it the max values for number of semaphores, number of tasks, number of mutexes, or is it mutices? Mutexes, a whole bunch of maximum values you have to look at. You must look at that file and change it to fit your condition. How many semaphores you're going to use, how many tasks you're going to use.
So if you say you want to use 6 and you only use 2, then
No, that's fine. That just means you waste a little memory. And since you got lots of memory for this lab, it's not a huge deal. But if you define 2 instead of use 6, that's a problem.
so we can't malloc our own.
Well, when I wrote this, malloc didn't yet exist for GCC. Now it does. But, you know, my feeling is that for a small CPU where you are the only programmer, you don't have to deal with some crazy user out on some terminal doing something to memory, malloc hardly makes sense. You may as well use static arrays because you're probably going to do stuff that's pretty static in size.
Can we use trucks though?
Sure, of course. You can use any C format variable you want. You can use structs. You can use unions. You can use any combination of instances, whatever. All the variables you define are going to be on the stack, probably. And so you have to make sure that you allocate enough stack size for the variable. Yeah.
So is a global variable defined on every stack, or does it have its own memory location?
Global variables have their own memory location. I'm going to encourage you to use as many local variables as possible because they don't have to be protected as much.
But you're getting billed 3 times for one.
Well, every task has its own value of a variable because, in some sense, it owns the machine. And so, yes, you have to get billed 3 times if you want the same variable in 3 different tasks. Yes, you're going to have 3 copies of it because that's the way it should be, unless it is supposed to be shared between them, and then it must be global. And you must protect it then when you read your write to it. Most of the bugs that I see in this lab come from people allocating more semaphores or more tasks than they have set up the tables to withhold. You must pay attention to the maximum sizes. Number of tasks, number of semaphores, plus. And then the second way of generating errors is you must protect memory locations with semaphores. I'm going to do examples of this. So don't go berserk. But you do have to protect stuff. Okay, final projects. Yeah.
Does Cornell reimburse us for our $75 budget that was spent?
I'll give you a hearty handshake. How's that? No, this is a $75 budget. It does not mean you have to spend the $75.
Well, let's say I just spent $20.
That's go for it. So, for instance, you're going to rent the STK 500 from me if it's for $15. I'm not expecting you to cough up $15 into my hand for that. That would be ethically doubtful.
Yeah.
And besides, it would be awfully hard to. There's no way to handle cash in the department in any reasonable fashion.
All right.
So that's funny. You're not paying that. I'm not getting that. But it's charging. I'm charging you $15 for the privilege of using it, unless you build your own prototype.
Yeah.
Right. So I expect that the actual money people spend out of their pocket is going to be a fairly small amount. I will spend up to $20 per group for people, for small parts. The department's been pretty good about covering that. First order will go in just after spring break. The rules are, it's got to be DigiKey. You've got to order from DigiKey, or maybe one or two other places. And the part numbers you specify have to be exactly correct. If they're not exactly correct, if I enter the part number into the search engine DigiKey and I get nothing, null, don't order it. I don't search, I don't scratch my head, I don't send you email. I'm going to get a lot of emails, folks. It takes me a couple of hours every Monday morning to do this. I don't have time to have a negotiation about, oh, it was supposed to be the -1. If you order something you can't solder, I'll order it anyway. It comes off your budget. I'm not going to check anything. You need to check it, or check with me before you order it. So you'll give me a parts list, not as a common delimited file, not as an attachment, not as a spreadsheet, in the mail file. And then I will put them into the search engine, order them up, and if you go over the $20 limit, I go right down lexically, order down the list until I get to $20, and after that I don't order. So, don't go over 20. And believe it or not, I can remember from week to week what the sum for a group is. So you get $20 total, not every week. I've learned that one.
The groups don't pay for shipping, right?
If I order it, you do not pay for shipping. If you order it, you pay for shipping. Shipping is not part of your budget, however. That means that when you blow out the chip the day before the demo, you can get one by overnight FedEx at $50, and I'm not going to charge you $50 for shipping.